All right, we are now going to start a discussion of reaction mechanisms, which are the actual chemical steps that occur in the process of a chemical reaction. So let's say, for example, we have this particular reaction here. Nitrogen dioxide in the gas phase reacts with carbon monoxide in the gas phase, and that produces nitrogen monoxide gas and carbon dioxide gas. So in this reaction, it looks like that an oxygen is just swapping positions. It's going from the nitrogen dioxide to the carbon monoxide. And let's say the rate law for this equation has been measured, and it's found to be that the rate is the rate constant K times the concentration of NO2 squared. And it's key for us to understand that the rate law must be determined experimentally. It cannot be found from the overall reaction stoichiometry. Now, what's interesting is this rate law gives us clues into what is actually happening in the chemical reaction itself. Now, when you look at this, you might think, when you look at chemical equations, you may think that this is just basically what happens is that an NO2 slams into a carbon monoxide, and that produces the products. But this rate law here actually gives us information that that's not what's happening. That's not the overall steps that are happening. So how do we do this? How do we use this rate law to give us clues into what might be happening? Well, what we do is we assume that there are certain what we call elementary steps that are occurring. Elementary steps are actual chemical events that occur. So what, for example, we'll do in this reaction is we'll say this occurs in two steps, two elementary steps. And in step one, what we're going to assume is that two nitrogen dioxide molecules collide and they form NO3 as an intermediate, NO3 gas, and nitrogen monoxide as an intermediate. And then in step two, what occurs is that the nitrogen trioxide that forms reacts with a carbon monoxide to form nitrogen dioxide and carbon dioxide. And what's interesting here is we are allowed to extract the rate law for elementary steps from the reaction stoichiometry of the elementary steps. And sometimes books to distinguish between overall reaction stoichiometry equations and elementary steps, authors will put a bold arrow like this to indicate that these are indeed events that are occurring, whereas this is just telling us where we're starting and where we're ending, and they're different. And a key way they're different is we are allowed to extract, like I said before, the rate law for elementary steps in the following way. In this case, we'd say, well, for elementary step one, the rate is going to be equal to K times the concentration of NO2 squared. And we would write it like this because there are two NO2s colliding. Because there's two, we take NO2 to the second power. And what we would do for the second step, we would say the rate of this second step is going to be equal to our rate constant times the concentration of the two things that collide, which in this case is NO3 and carbon monoxide. Now, what we want to make sure that we do is we're able to add these two steps together to give us the overall reaction stoichiometry. And indeed, we can see that we can do that, because if I take the reactants and products in these two reactions, notice I get an NO3 out, but that NO3 is consumed. So anything that's on the reactant and product side in the same identical chemical and physical condition can be canceled out. And you see I can do that again here with NO2. There's an NO2 here and an NO2 here. And what I'm left over with is an NO2 on the reactant side plus a carbon monoxide on the reactant side goes to a nitrogen monoxide on the product side and a carbon dioxide on the product side, which you will note is the overall reaction. We've got to be able to do that. We would note that the rate, the overall rate for this reaction should be the rate of these two steps combined. So the overall rate for this reaction is going to be K times the concentration of NO2 squared. That's the rate of the first step, plus the rate of the second step, which is K times the concentration of NO3 times the concentration of carbon monoxide. And we're going to need to designate these rates as being, rate constants as being different from one another. This is the rate constant for the first step. This is the rate constant for the second step. Now, if the second step is extremely fast compared to this, let's say this step takes a really long time, and this is lightning fast, the amount of time that this step takes is essentially zero. It's like an insignificant addition because it adds a very little amount of time to this particular process. Once this happens, step 2 happens like a rocket. And if that's the case, then we will find that the overall rate for the reaction would be K times the concentration of NO2 squared, which is indeed the rate law for the overall reaction that we experimentally find. And so what we can say is that this reaction series of elementary steps, if this step is slow, step 1 slow, and step 2 is fast, if we assume this with this slow and this fast, then those assumptions are consistent with what we find experimentally. And because our mechanism, this is called a mechanism, our kinetic mechanism fits with what's observed experimentally, we say we have a proposed mechanism for the reaction. Now, these can never be proven, but what you can do is you can say this mechanism is consistent with what we observe, and that's the best you can do. Some things you could do to look for more evidence that this is indeed the mechanism is to see if you could detect, for example, the presence of NO3. If we could set up this reaction in a flask and we could indeed detect the presence of NO3, that would supply more evidence that this mechanism is correct. Okay, we're going to continue on with mechanisms. We're going to consider the following overall chemical reaction. Note this is not a mechanism, but rather this is the overall reaction stoichiometry, where we have nitrogen gas reacting with oxygen gas to form dinitrogen oxide and ozone, all in the gas phase. And we'll say it is said to proceed by the following mechanism. A molecule of oxygen gas splits into 2 singular oxygen atoms. Now, since this is a mechanistic step, so we'll draw in the bold arrow here, remember that we can assume that the rate for this is based on the reaction stoichiometry of the reactants. So we'd say this is K1 for step 1 times the concentration of oxygen. And because there is only one reactant, we call this a unimolecular step. We'll say step 2 is where a molecule of nitrogen reacts with one of these oxygen atom in the gas phase that has formed. As you can imagine, these are probably transient. They don't last very long. That's very unstable. And that's going to form N2O in the gas phase. The rate here would be for step 2 times the concentration of N2 times the concentration of oxygen atom in the gas phase. And because there are 2 reactants, we call this bi for 2 molecular. Bimolecular. So step 1 is a unimolecular step. Step 2 is a bimolecular step. And then in step 3, we're going to have a termolecular step where three things collide. That's going to be an oxygen atom in the gas phase, a molecule of nitrogen, and a molecule of oxygen gas. Those are going to collide in an actual chemical event, and that's going to form ozone, and the nitrogen is going to remain the way that it was. And the rate of this step, we'll call this K3 because it's the third step, and it's going to depend on the concentration of our three reactants: gas phase oxygen atom, nitrogen gas, and oxygen. And this again is a termolecular step. These are very rare, just like it's very difficult to get three cars colliding simultaneously. It's tough to get three molecules colliding simultaneously. A two-car crash, that's much more likely. Again, this is occurring at the same instant. As far as we know, a tetramolecular step where four things collide has not been observed. These are called the molecularity of each step. So the molecularity of step 1 is unimolecular, with one thing collides. The molecularity of step 2 is bimolecular, where two things collide. And the molecularity of step 3 is termolecular, where three things collide, and these are rare. We're also going to use the term intermediate to describe chemical mechanisms. They're usually quite reactive, and we can see an intermediate is going to be a species like these free oxygen atoms that are produced in the middle of a chemical mechanism, but are ultimately consumed. You can see here each oxygen that forms ultimately ends up being consumed. And so we would call, in this particular mechanism, oxygen atom is a reactive intermediate. Another way we can say this is present in the mechanism, but not the overall reaction stoichiometry. Present in mechanism, not in overall equation up here. You see the oxygen atom is not up here, not an overall reaction. And again, notice these intermediates can be somewhat exotic, like free oxygen atoms. Those are highly reactive, and those are only going to exist for a short period of time. A special type of substance that shows up in chemical mechanisms is known as a catalyst. Catalysts are going to be substances that are going to speed up a chemical reaction. So their presence speeds up a chemical reaction, makes them occur much more quickly. Now, reactants also speed up chemical mechanisms, right? If you have reactant present, the higher the concentration of the reactant, we know the higher the rate of the reaction. But in contrast to reactants, catalysts are not consumed. So catalysts are not consumed, whereas, of course, reactants are. In biological systems, catalysts are called enzymes. And catalysts can be in the same phase of the reaction, so we call these homogeneous catalysts. These would be catalysts that are in the same phase, dissolved, aqueous. Maybe they're both solids, maybe they're both liquids. Usually they're both just aqueous. So if they're in the same phase as the reactants, so these are in the same phase, or they can be heterogeneous. You can have a heterogeneous catalyst. And this is going to be in a different phase than the reactants. An easy example of a heterogeneous catalyst is Coke and Mentos. In the Coke and Mentos system, what you have is aqueous carbon dioxide. So carbon dioxide that's dissolved in solution, and it comes out in the gas phase. So you have dissolved phase carbon dioxide, and what you do is you add Mentos candies, and Mentos candies have all these little pits and pockets in them. I'm just going to exaggerate here, make like a groove in the Mentos. And these pits are little air pockets they have. So these are little gas pockets. And so in this case, what happens is the dissolved carbon dioxide that's in the aqueous liquid phase, they diffuse into the gas phase. So we see that the catalyst, which is the air bubble on the Mentos, is in the gas phase. That's in a different phase than the reactants, which are in the aqueous phase. And catalysts act by lowering the activation energy of a reaction. So if we have a reaction here, remember we go from reactants to products, and this is energy on this axis, and this is how far the reaction has proceeded. So we call this reaction progress. Of course, as the reaction progresses, it goes from reactants to products. We could imagine in the absence of a catalyst, you'd have an activation energy barrier that looks like this, whereas in the presence of a catalyst, that activation energy barrier is going to be much lower. So your activation energy barrier in the presence of a catalyst would be low, and in the absence of the catalyst is going to be high, and this effect causes the reaction to proceed at a much faster rate. So let's see how this might happen. How might it be that a catalyst could speed up a chemical reaction? Well, let's imagine we have this particular chemical reaction. 2 cerium-4 ions dissolve, so all this is going to be aqueous phase, reacts with the thallium-1 ion to form 2 cerium-3 ions and a thallium-3 ion. So this is our overall chemical reaction. And this is observed to be slow. And the rate law of this particular chemical reaction in the absence of a catalyst is observed to be the following. The rate is equal to our rate constant times the concentration of cerium-4 squared to the second power and thallium-1 to the first power. And so you should be able to see that this rate law is consistent with a termolecular process where 2 of these have to collide with 1 of these to go to products. And we know that that's very unlikely. We know that termolecular processes are rare. That's because it's tough to get 3 things to collide at once. So it makes sense that overall this reaction would be slow because 2 of these have to collide with 1 of these. This is one of the cases that happens sometimes where the actual mechanism and the overall stoichiometry match. So it's a termolecular process, a termolecular mechanism. It's slow. However, if we add some manganese 2 as a catalyst to the mixture, it speeds up drastically. So this is how we would write the reaction in the presence of a manganese catalyst. So our 2 cerium, this should be thallium-1. 2 cerium-4s react with thallium-1. And we write manganese 2 over the top. That's how we do this as a catalyst. That's how we write catalysts in. That's going to form our 2 cerium-3 ions and our thallium-3 ion. This proceeds by a different mechanism than 2 of these and 1 of these colliding. And here's how it works. We have a cerium-4 ion That's going to react with a manganese 2 ion, and that's going to form a manganese 3 ion and a cerium 3 ion. And we'll say this proceeds at rate constant K cat for K catalysis. And this is the slow step, by the way. So the slow step, that's going to be the one that drives how fast the reaction occurs. And then the next two steps occur very rapidly. A cerium 4 ion will react with a manganese 3 ion. The manganese 3 ion that formed, this will proceed at step we'll call K1, and that's going to form a manganese 4 ion and a cerium 3 ion. And then finally, the manganese 4 that forms is going to react with the thallium 1 reactant. Thallium 1 reactant. That'll react with this manganese 4 that formed. We'll say this is step K2. And you're going to produce manganese 2 ion, sorry about that, plus thallium 3. And if this were the case, if these steps occurred very quickly, our overall rate would be dependent only on this step, which would have the rate constant times the concentration of cerium 4 times the concentration of manganese 2. So we see the catalyst shows up in the rate law. And indeed, when these reactants are mixed with some manganese 2, this is the rate law that's experimentally observed for this particular reaction catalyzed by manganese 2. And so we can say that this mechanism is consistent with this rate law, with the experimentally determined rate law. And what's nice about this, if you look at this, you can see, I'm going to go ahead and underline here in a different color. You can see that manganese 3 is generated in the first step and consumed in the second step. So we would say that manganese 3 is a reactive intermediate. We also see that manganese 4 is generated in the second step, but consumed in the third step. So manganese 4 would be another reactive intermediate. And if we cross these out, we can do that because, you know, they don't make any difference in the overall change in the reaction. And we also notice that the manganese 2 that is consumed in the first step ends up being regenerated in the last step. And that's got to be true of a catalyst. Remember, catalysts are present in the mechanism. It shows up here and here, but it's not consumed. And so in this case, we can cross out the destruction and production because overall there's no net change. And look what ends up happening. We're left on the reactant side with 2 cerium 4s and a thallium 1. On the product side, we produced 2 cerium 3s and a thallium 3. And so it's easy in this case, I think, to see how the addition of a catalyst can speed up a chemical reaction, because in this case, it changes a termolecular step, which is very unlikely. And even though you've got all this stuff mixed together, it's not going to happen that often. And so it's going to be a slow reaction. But by the addition of manganese 2, you change the mechanism into a series of bimolecular steps, 2 things colliding, which is much, much more likely. And so, of course, the reaction speeds up.